Pluto, the enigmatic dwarf planet residing at the outer reaches of our solar system, is stirring up excitement within the astronomical community. Recent reports hint at a possible encounter with Neptune, raising concerns among scientists and space enthusiasts alike. Renowned experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the potential consequences of this celestial clash. But how did Pluto end up on a collision course with its distant neighbor, and what might this cosmic collision mean for us here on Earth? Let's explore this unfolding event. Once considered a full-fledged planet, Pluto was later reclassified as a dwarf planet due to its unique orbit. Despite this change, it continues to captivate and engage astronomers. Recent predictions from prominent scientists highlight a worrying proximity between Pluto's path and that of Neptune. These experts caution against a potential collision between the two planets, posing a significant threat to Earth. Pluto's journey around the Sun is marked by its unparalleled characteristics within our solar system. Its orbit spans an extensive 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its intrigue is the highly elliptical shape of its orbit, a departure from the nearly circular orbits of the major planets. Additionally, Pluto's orbit is inclined at 17 degrees to the ecliptic plane, making its path steeper compared to other planets. One notable aspect of Pluto's orbit is its intersection with Neptune's path. For approximately 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their respective positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational influences exerted by other planets. The examination of Pluto's orbit commenced shortly after its discovery, presenting a puzzling trajectory for astronomers. Unlike the majority of planets whose orbits align relatively close to the ecliptic plane, Pluto's distinctive features include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amid these intricacies serves as evidence of the complexities inherent in space mechanics. The three-body problem in space involves understanding the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem elucidates the intricate interplay of their paths and gravitational pulls. Terms like azimuthal libration, latitude libration, and the VZK oscillation contribute to unraveling this celestial puzzle. Astrophysicists assert that azimuthal libration, responsible for maintaining planets in their orbits, plays a vital role in the context of Pluto and Neptune. This term signifies that when Pluto intersects Neptune's orbit, it is positioned at least 90 degrees away from Neptune, crucially preventing potential collisions. Latitude libration ensures that when Pluto approaches Neptune or other giant planets, it is situated significantly above their orbital plane, providing an additional layer of protection against collisions. The VZK oscillation explains why Pluto's orbit around the Sun appears unusual but remains smooth over time despite apparent randomness in space. Numerical simulations in the late 1980s revealed that despite stable properties, Pluto's orbit is technically chaotic, with minor initial deviations leading to significant differences over millions of years. However, Pluto's unique orbit maintains stability over incredibly long time scales, keeping chaos in check. Recent computer tests have enhanced our understanding of how large planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto, significantly contributes to the stability of Pluto's orbit. Additionally, Jupiter's immense gravity exerts a substantial influence, while Saturn's impact, though smaller, also plays a role. Through comprehensive tests, scientists have shown that the combined effects of Neptune, Jupiter, and Saturn ensure the safe and stable movement of Pluto in space for billions of years. These phenomena are essential for maintaining the order and predictability of celestial movements in the universe. Without these mechanisms, the solar system would be prone to greater chaos and unpredictability, potentially leading to collisions or ejections from stable paths, causing ripple effects on other celestial bodies. Understanding Pluto's orbit is particularly crucial amid discussions about a potential collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of the solar system. Pluto's case highlights how seemingly unstable orbits can reach equilibrium through the intricate interplay of gravitational forces and orbital mechanics. Continuous observation and study of these phenomena are vital for gaining a better grasp of our position in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a prime example of this unpredictability. The concept of orbital chaos vividly illustrates the sensitive dependence of a celestial body's path on its initial conditions. As demonstrated in Pluto's case, even slight variations in the dwarf planet's position or velocity can significantly alter its long-term orbit. Computer simulations have been instrumental in helping scientists understand how Pluto moves in space. By making small adjustments in these simulations, astronomers can observe how minor tweaks can have a substantial impact on Pluto's trajectory. In the late 1980s, these simulations revealed an intriguing aspect of Pluto's path. Despite features like azimuthal and latitude libration contributing to its stability, Pluto's orbit can still exhibit unpredictability. Even a tiny initial difference in Pluto's position or velocity can lead to significant changes in its path over many years. Despite this inherent chaos, Pluto's orbit remains stable for an exceptionally long time, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows a structured order. Predicting cosmic events, especially with planets like Pluto that have unpredictable orbits, is quite challenging. The inherent unpredictability of these systems makes long-term forecasts uncertain. Numerical simulations help us understand and anticipate the future paths of celestial bodies, but they also reveal the limits of our predictive abilities. These models heavily depend on accurate initial conditions and simulate complex interactions. Even a small error can lead to significantly different outcomes, making precise predictions difficult. The chaotic nature of celestial orbits such as Pluto's reminds us of the ever-changing universe. While we've made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational influences of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how each planet's presence and position can affect the stability and trajectory of other bodies in the system. Despite these complex forces, major astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. This raises questions about why such a collision, which seems unlikely given these intricate dynamics, is now a topic of concern. Neil deGrasse Tyson, a well-known astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly regarding Pluto. Tyson, famous for advocating Pluto's reclassification as a dwarf planet, shares insightful thoughts on how our understanding of celestial mechanics is always evolving. He sees Pluto's reclassification not as a demotion but as a necessary adjustment to our increasing knowledge about the various objects circling the Sun. Michio Kaku, a well-known theoretical physicist, also weighs in on this scenario. He emphasizes that understanding Pluto's orbit is essential for space exploration and predicting potential hazards. Kaku suggests that studying celestial mechanics such as Pluto's relationship with Neptune can even provide insights into the fundamental principles of physics, including string theory. While the chances of Pluto colliding with Neptune remain low, the discussion highlights the unpredictable and intricate nature of celestial mechanics. Ongoing research and simulations will continue to refine our understanding of Pluto's orbit and its long-term stability in our ever-evolving solar system. The study of celestial mechanics, particularly regarding Pluto's orbit and its interactions with Neptune, continues to challenge and refine our understanding of gravitational dynamics. While the three-body problem offers a mathematical explanation for the stability of Pluto's orbit, the broader implications of these orbital interactions extend to planetary formation, evolution, and even potential space exploration. Despite the apparent chaos in Pluto's orbit, its long-term stability is secured by a well-established resonance with Neptune. This 3:2 orbital resonance, where Neptune completes 3 orbits for every 2 of Pluto's, ensures that the two bodies never come dangerously close to each other. This phenomenon highlights how gravitational forces can create order out of seeming randomness, a principle applicable to various celestial systems. Furthermore, this type of resonance is not unique to Pluto and Neptune. Other examples include Jupiter's Trojan asteroids, which remain in stable orbits due to their interaction with the gas giant's gravity, and Saturn's moons, some of which exhibit resonances that influence their geological activity. Understanding these mechanisms provides insight into planetary dynamics both within and beyond our solar system. Modern astrophysics relies heavily on computational simulations to model celestial interactions over vast timescales. Simulations of Pluto's orbit suggest that while small variations can lead to seemingly chaotic results, the overall structure remains stable over billions of years. These simulations help scientists predict planetary motions with remarkable accuracy, offering insights into potential changes in the solar system's architecture over millions or even billions of years. However, these models also underscore the limits of predictability. Even with today's advanced technology, minor inaccuracies in initial conditions can lead to drastically different outcomes over long periods. This sensitivity to initial conditions is a hallmark of chaotic systems and reminds us of the inherent complexity in predicting long-term cosmic events. The dynamics observed in Pluto's orbit offer valuable parallels to exoplanetary systems. Many exoplanets, particularly those in tightly packed systems, exhibit resonant orbits that help maintain stability despite gravitational interactions with nearby planets. By studying Pluto and its relationship with Neptune, astronomers gain a better understanding of how exoplanetary systems form and evolve, improving our ability to detect and study distant worlds.